So, welcome everybody. Please have a seat. I hope that you in the other room can hear me as well. Can someone maybe confirm that? Yes. Can everybody hear me in the other room and in this room? Okay. Good. And can the other room also see the slides of the PowerPoint of Nick? I don't hear anything, so I guess no word is good word. So again, welcome everybody at this session about the future of energy. I'm sorry for the delay with starting up. As you can see, we are divided into two rooms. And this, because we wanted to divide the speakers so that all the audience can have the experience of having a live speaker in front of them. I hope it will work out. We have a good technical team with us who will make sure that we can hear and see the other room when we have the discussion. So my name is Janne. I will be the chair for this plenary session today. I'm very honored to be here with all of you. And before I start, I wanted to thank also the help of the volunteers of the technical team who will help us with the questions and all the technical issues. So we will start this session with a talk from Nick Lopez Cardoso, who is sitting here with me in this room. And yeah, Nick is a professor of science and technology of nuclear fusion at Eindhoven's University of Technology in the Netherlands. And he will talk about nuclear fusion and the future of energy. And after Nick has spoken, Mario Giampietro and Emilio Padio-Schioppa will follow with their talks on abundant and cheap energy and its consequences. And Mario Giampietro and Emilio are in the other room, speaking there. And Mario is a research professor at the Institute of Environmental Science and Technology of the University Autónoma de Barcelona in Spain. And Emilio Padio-Schioppa is an associate professor of ecology at the University in Milano. And after that, we will link to another topic about energy sufficiency. And Yamina Sahed will speak. She will join us online because she was unfortunately not able to make it to Pisa. But she is here on the live stream, so also welcome to you, Yamina. And Yamina, Dr. Yamina Saheb is a senior energy policy analyst at OpenExp and a lead author of the IPCC sixth assessment report on climate mitigation, and also a lecturer at Sciences Po in Paris on climate risk. So at the end of these 4 talks, we'll have time for a discussion. And I already know that we will go into the break time, but I hope you will stay for some interesting discussion and questions. As you can see, there is pieces of paper on each of the rows because we chose to do the questions on paper. You can write them during the sessions, and the student volunteers who are in the blue shirts, there's 2 or 3 in each room, will collect the questions in between the talks very briefly, but also afterwards. And I have help of 2 dear friends who will go through the questions and select interesting ones for the discussion. You can, of course, ask questions for clarification, but I ask you please to save the questions about the content for the discussion afterwards so we can go quickly through the talks first. So, to start off, I would like to invite Nick Lopez Cardoso to the stage, who will start. We will start with a brief interaction, actually, with the audience before he will start his talk on the potential of nuclear fusion. So welcome, Nick. I will hand you the microphone.
Thank you, Anna. I'm very tempted to ask, because there are 2 rooms, so I am kind of also speaking to the other room, and this was arranged so that everybody could have the privilege of seeing the speakers live, but the rooms are next to each other. So we could all also move as the audience, and we could all have the live speaker experience. So it's just a suggestion. At least I'm here. I'm happy to see you here. Can I just, before we start, maybe just so that I can pace my talk a little bit, ask who of you would say they have a basic knowledge about nuclear fusion, nuclear? Yes. Okay, good. Like maybe 1/3. Who of you would say I could easily lecture a couple of hours about it? Oh yeah, really, very good. But I'll go through a few of the basics very quickly. My talk is half about fusion, and then it comes to the question, when can we have it? Anyone here? Yes? Okay. The question is, when do you think we can have it? Good. Never. That's a very precise answer. Yes. 2038. Okay, great. Yes, please. Okay. Yes. That's the running joke, right? Yeah. It's always 50 years ahead. Okay. Well, my talk is going to give you some very tangible answers, I hope, because this is really what it's about. But before we go into the when, so then I'll do a little analysis, which I then also apply, which is more like an economic analysis, to other energy sources, and we'll see. Okay, well, we'll see what comes out. I hope that'll be of interest to everybody. So I'm going to start, at the risk of boring everybody, with a picture that sets the stage, because I know in your society, so to speak, it's the question really starts by how much energy do we really need? And this is something I should like to address. And also, we start with, is energy really the problem, or is the problem much bigger, or is energy even a problem? So, I have a little picture here, which I made years ago. There was a time when this worked. Yes. Okay. Yeah. Well, let's assume that this works. So this is a very long time scale, starting at the year 0 and running three centuries. And as we all know, the population was very small for a very long time, and then it started to run up. And yes, we are in this ridiculously steep slope where everything is changing very fast. So if you think that we live in a dynamic time, that's correct. We do live in a very dynamic time, and it's much more dynamic than it's ever been. Okay, so and somehow we hope that the population will stabilize by natural means. And then, of course, we also know that the energy use per capita, so to speak, has been very low for a very long time, and then suddenly it should shut up. Well, it's obvious because there's more of us, and each of us is using more energy all the time. But you can reverse that relationship. You could also say it was only here when we started to learn how to use that energy that we could provide for more people and for a good life for more people. So it was the energy abundance that drove up the population. And by implication, you would say, okay, but we need all that energy to support that population. Now it gets a little bit nasty, because the other question is, okay, if we didn't have all that energy, would we be able to support so many people? Well, we know how we make the energy. It's by burning fossil fuels, almost all of our energy. And we have to stop doing that. This is something that's very clear. And we have, well, now the idea is that we stop doing that, well, certainly within this century and preferably before 2050. So it gets even more dynamic now. We are in the phase where fossil has to go down. It's like 80% of our energy supply. And in the meantime, the energy demand is growing. So I think it's without question that there is an issue there. If you ask, so this is a picture you probably all know. It's very old in the meantime, but it's still useful to see that countries use per capita the energy used per capita goes up. If this very useful bar in the bottom, this hiding part of my slides. So there's the energy used, there's the per capita GDP. Yeah, I think it doesn't want to go away. Yeah, okay. And there's an almost linear relationship, but at some point, if you're rich enough, there's this rollover that we all know about. Sometimes it's sold as an increased energy efficiency, but what we really see, in my opinion, is that down here in the linear phase, countries are using energy to increase their basic standard of living, making stuff. And at some point, we have everything we need. And then we start selling each other therapy, which doesn't need so much energy. Good. So that slope corresponds to 50 cents per kilowatt hour, which means that a country needs, if a country wants to get richer, what it needs to do is make more energy. And it's a very profitable thing because you can make a kilowatt hour for a few cents, certainly with fossil. So there's a huge gain there. Now, the unfortunate thing is that 4 billion people live somewhere there. And those 4 billion people, we all hope and expect to move up along that line. And in the meantime, those 4 billion people will become 7 billion people. Rough numbers, of course. And if just this happens, and all of us who are up there go back to that same circle, then still we need about twice as much energy as we have today. So I think that's sufficient setting the stage for the question, are we ever going to make sufficient energy to even power the basic needs of so many people? And how are we going to do it in a sustainable way? And if we don't, if that curve does in fact go down, would that mean that the population goes down too? I see lots of students or young scientists in this room. This is going to happen in your lifetime. So it's not an interesting academic question. It's something that's going to affect us all, and certainly our children and grandchildren. Now, you may not be so enthusiastic about the global domestic product or things like that, but there's a very basic thing here. A barrel of oil, which you buy for about $100, has the energy equivalent of about 20,000 person hours of labor. So it's a bargain. It's incredibly cheap. I mean, if you could have someone work for you for 20,000 hours for $100, would you say no to it? So this is very basic. How are we going to provide that energy? Well, jumping ahead, so to the title of the talk. So there's one technology of which we know there's in principle, in physics, in theory, it's possible, and it's the one source that we have not made to work on Earth. Every other known technology, known physical process we have, this one we know it exists, we haven't made it to work. Nuclear fusion is the process that powers the sun, powers the stars. It is actually the only power source in the universe. All the rest derives from it. It's also the source of matter. So it starts with light atoms, nuclei, hydrogen. They melt together if they're hot enough. And if the pressure is high enough, like in stars, they melt together and become bigger. So you get helium and up and up and up. So the stuff we're all made of is the result of nuclear fusion processes. And the interesting thing about it is that by fusing hydrogen isotopes, you can free a lot of energy, like 10 million times more, a few million times more than in a chemical reaction. Which means that if you could make a reactor like that, and you made it produce like a gigawatt, so comparable to a big coal plant, the amount of fuel that was needed per year was a few hundred kilograms. And you could store the fuel for that process for years, and it's not even dangerous, it's just lithium and water. Lithium, the kind of stuff you have in the batteries in your laptop or car. You could store it for years, so that would give you energy independence. So where we are today is that the world is building a machine called ITER, just ITER. And it's a collaboration of a lot of countries, as you can see, half the world roughly. It's interesting because it was started as a peace project, and today that's even very, very relevant too, as you can imagine. And ITER is meant to produce, well, it's an experiment, it's a scientific experiment. Oh, sorry, it's a scientific experiment. It's not going to produce electricity, but it's going to demonstrate that you can produce a few hundred megawatts of fusion power. Okay? So, why do all those countries want the fusion? Well, because it's totally safe, that it is. It doesn't emit CO2, of course. It gives you this energy independence because you can store the fuel for a long time. For the world, security of supply, well, there's enough lithium and water for a very long time. Now you might think, okay, but the lithium is going to be bought up by the car manufacturers to put in batteries. That's fine. We'll buy the second-hand cars and take the battery out because we need so little of it. And there's no proliferation issue, so okay, we can talk about that later. There's a drawback because it seems like ideal. What is the drawback? Well, it can't be done. If you think about it, how difficult this is, it can't be done. Well, if you say that to an engineer, they'll say, now I get interested. So now it's a challenge. And let me very briefly take you through a few of the challenges. So there's your reactor, and just to the pink stuff inside is the hydrogen fuel, but it's at a very high temperature. It's a temperature of 150 million degrees. 150 million degrees. Okay, that's like 10 times hotter than the core of the sun. First we had to learn how to deal with such high temperatures. And then you realize, okay, that you probably cannot put in a box. So you have to take it, to keep it together with magnetic fields. So that is looking at the sun, the coronal lobes, things like that. You learn how to do that, okay? We can do that, by the way. It's a solved problem. Then you have that very hot stuff. You should be worried about energy losses, as you can imagine. If you have something that is at a temperature of 150 million degrees and it's sitting right next to something that's at 4 Kelvin, energy transfer is going to be an issue. And we cannot tolerate much turbulence. So we had to learn how to control the turbulence. We did that. Then if you get all of that right, you're going to produce a lot of energy in a small volume. So somehow the walls are going to suffer high heat loads. You have to deal with that. Then a lot of the energy is released in the form of neutrons. So the first wall that sees that those neutrons has to be made of a material that can handle those neutrons. Okay. Then there's a bit that I won't go into, but we bring lithium to the reactor, but then there's an internal cycle where the lithium is transformed into a hydrogen isotope tritium. So a fuel cycle, that is actually a very complex process. And then there's a last challenge, which you might not have thought of, but this machine has been advertised as the most complex device ever built by mankind. Well, that's the worst thing you could say about something that should be an energy reactor. It should have been the simplest thing, but it isn't. It is the most complex thing, so we have to learn how to deal with that complexity. Okay, so how have we been doing? Well, again, so you see this picture ends in 2000, and that is not without a reason, and I'll tell you in a minute. But before that time, the progress in the power multiplication factor, which it's all about, so it's something that should be larger than 1 before you can sell anything, has been doubling very fast, faster than Moore's law, actually. So if you extrapolate that blue line, you'd get to a point which should be this machine that I introduced earlier, ITER. And we should have had it in 2004, but we didn't. Well, also, there are all sorts of reasons for that, but it's been postponed. And now it's meant to start operating, well, in a couple of years from now. It's being constructed, it's being put together as we speak in Cadarache in the south of France, not far from Aix-en-Provence. Yeah, so didn't we learn anything? Is that stagnation? Well, it just means we didn't make any bigger machines, because with bigger machines you get better performance. But we did learn a lot in the meantime. The knowledge base has increased enormously in those 20 years. Yeah. So recently, you might have seen in the newspapers or so, television, whatever, that, yeah, there was some progress. Yeah, so it's still, we are still moving, but the real spectacular thing is that suddenly there are startups that think, with all the progress that's been made during those 20 years in understanding, in better materials, in better magnets, we can actually build commercial fusion power plants now. And this is just one example, and I should like to show a clip of an interview with Bob Mumgaard, who is the CEO of a startup that was spun out of MIT. Well, I'll just let him speak.
We like to be optimists. Imagine a world in 2050 where you've got 10,000 fusion power plants producing 20% of the global energy use without getting any carbon. That would be really good for everyone.
That's going to be all the sound there is. So, yeah, 10,000 fusion power plants by 2050. So that was an answer to your suggestion that we have to wait 50 years. Now he wants to have 10,000 by in 25 years from now. Okay, and you think, well, I'm not going to believe that. But some other people think, well, why don't we put a couple of billions in there? And those are private investors who actually think it's an interesting idea to start putting money in that. So they are getting a few billion to realize that idea. And this is not the only startup. So they're about 23 at the moment, or even 30, I believe, that are getting serious money. Some are still at the millions level, but in total, the private funding for fusion development is exceeding that of government funding. So here you see the number of private companies. It's growing all the time. So that is a really new development. Let's go back to the roadmap of this government-funded mainstream program. This is the official roadmap of the European program. And you see it has this ITER machine, and after the ITER machine, it wants to build a demo machine. And the timeline is that ITER should start operating in a couple of years from now. Then it should have its full performance in, well, 10, 12 years later. And that would kickstart the decision on demo, which can then start construction somewhere in the early 40s. And it has to be built, and it has to reach full operation. So somewhere 2055, 2060, you might expect a demo to work. Well, whatever you think about it, it means no electricity from fusion before 2050. And yeah, so that's why we got all those startups. They say, well, surely we can go faster than that. Yeah, so you see there's a lot of, just look at the little pictures, you'll see that they're all very different concepts. So this is the exciting thing about it. All those companies think, the knowledge base is so big, we can now put our own concept together. And a lot of different concepts are being tried out. Yeah, so this is a picture that was made by the Fusion Industry Associates, showing that indeed there's a vast variety of different technologies that are being tried out at the moment with the private funders. Okay, so all of them say we'll be smarter and smaller and cheaper and sooner than the mainline program. There are lots of different concepts being tried out. They get a lot of private money. If you ask me to give my opinion on each individual one, for most of them I'd say, don't know about that. But together, I mean, if one of the 30 is successful, that would be a big success. So why can they claim that they can go so much faster than the government program? Well, for one thing, so I made a spider diagram here, which with the sort of technology milestones that you have to achieve to make a full-blown fusion reactor. And the red bit is if you want to build something that works for a day, basically. The green bit is if you want to build something that works for months or a year. And then there's the lifetime technologies that for if you want something that works for 30 years. And the government program says, let's build a machine that ticks all the boxes. And the startups say, well, let's first build a machine that works for an hour or for a day. And we already do a little bit on the other things. And then we push that and we get better at all of it as we go along. So, and here's like the philosophy that we have to realize. If your goal is to build 10,000 plants, then you should say, okay, the first 100 or so, 10 or 100, we only built to learn how to do it. And we can try out all sorts of things in order to get the best technology once we start to roll out the deployment. Yeah. So it sounds a little bit strange, but because these things are so expensive, but in any other product, you would say, yes, of course. You make a lot of tries before you start the big production. Good. 10,000 power plants. Is that even possible? Is that even realistic? Let's just do a very basic calculation and say, okay, 500 per year. So if you want to build them in 20 years, that means 500 per year. Well, that is a big number by any standard. If they cost a few billion each, that would be an industry that is 50 times bigger than the fission industry today. And it's a few % of the global domestic product. That is a big industry. It's 10 times bigger than Apple, for instance. And so the suggestion is that we built that in a couple of years. Okay, and then there's another thing. So if we were building 500 power plants per year for 20 years, then the industrial capacity that needed to be built up for that, okay, here we go. Yeah, so maybe I should introduce this. So if you want to build up a park with power plants and you want to get to a steady state, the fastest way to get there is a straight line, of course. But the straight line should have a production capacity that corresponds to the replacement once you're in your saturated states. So there's a relation between the saturated state and how fast you can go in the linear phase. Okay, so if you want to go too fast, very obviously in 20 years you built your 10,000 plants and then they still live for 30 years and there's no need to build new. So that industry would have to be built up to something that is ridiculously large, and then there's no business for 30 years, and then you would have to repeat that trick. So you get an oscillation. Well known in industry, of course, that you have to match the demand to match your production capacity to the demand. Okay, so I think there are reasons to say that this is not very easy to sell. But then go back and think, okay, but we had to solve a problem. This was only one of the possible solutions. But wouldn't this same thinking apply to every technology that we want to roll out to achieve the transition to sustainable energy? And yes, so if you just think through, if you have a new technology, and suppose you had something in the lab that produced a megawatt, not fusion, just whatever you like. Before it makes an impact on the global scale, you need to have something that produces about 100 gigawatts. It's just tiny still on the global scale, but visible. So with a doubling time, if you start to grow that exponentially, with a doubling time of 2 years, that takes tens of years. Yeah, and only then are you at the start of your linear phase. Now that may sound dramatic, but this is exactly what has happened, for instance, with solar panels. They have been growing exponentially with a doubling time of 2 or 2.5 years for the past decades, and they're starting to roll over now. This is a log plot, so the linear bit here is exponential growth. This is a linear plot, so you see that exponential foot is tiny, and it's only now starting to grow. I'll get back to the saturation later. Yeah. And there's some questions. If you want to grow so fast, how do you implement innovations? Aren't you afraid of technology lock-in? Are we happy with the solar panels we have now? Or in retrospect, could we have developed better ones and made those cheap? And let's go back to fusion now. But let me just dwell a little bit on that picture. So I said, if you want to get somewhere, and we have a fair idea where you want to end, because you want to power like tens of percents of the world energy demand. So there's your end level. You say, I want to get there with a straight line, and the slope of that line corresponds to your industrial capacity. It's not an assumption, it's just a mathematical identity. And you'll see that, yeah, if you start building with that industrial capacity here, then at some point, the ones that you build here will go out of operation there. So you get your rollover. Yeah. Of course, on day one, you don't have that industrial capacity ready. So you have to build that up. And typically, historically, for many other technologies, you see that that is approximately exponential. So there we go. And of course, if there's a smooth foot, then you get a soft corner there too. And we can put equations to that. Aha, this computer doesn't handle Greek symbols very well. But you can calculate where the transition happens. And yeah, so now it depends on two timescales. The timescale of this linear, so that's the lifetime of the product, and the exponential growth phase here. And I bring this out because for something, if you build something that lives long, like a solar panel or a wind turbine or a fusion power plant that lives 30 years, 40 years, 50 years, and your exponential growth has a doubling time of a few years, it means the rollover is very early. And then there's still a lifetime of linear growth to come. If you sell smartphones with a lifetime of 2 years, you don't have to worry about the linear phase. You go exponential all the way to the top. So there's an essential difference between deploying short-lived things and long-lived things. Okay, so if we compare the log plot as I did earlier with the linear plot, you'd see that in the log plot, it seems to be all about the exponential growth, which is very spectacular. And this is indeed where a lot of the development happens. So, in fact, everything is still small, so the investments are manageable. You also have, because it's still small, you have to realize it's irrelevant for generation. It's really about developing the new technology and making it ready for fast rollout. And once you achieve that middle bit of the S-curve, yeah, then the investments become very big, and you're a bit too late for radical innovations now. Then you would have to start over. Okay, so let's apply that. That's a bit unfriendly. There we go again. If we apply that same logic, the same equations to renewables, you'd see, okay, yeah, they follow that line pretty well. And they seem, with the present data, this is IEA data, yeah, it says there, it seems to saturate at a certain level that you can already foresee coming because these things have a lifetime. Well, this is straight from the IE side, so you see, it really looks like it has entered the linear phase for both PV and certainly also for wind. And why is that? Because it's way too early. We should have grown exponentially much further before leveling off. And now you look at investments and you see, hey, the investments in renewable technologies, in particular for wind, onshore, and solar, have stalled already for 10 years. They've been together about 350 billion per year. And of course, we know since the Stern Review that in order to make that transition happen, we need to spend a few percent of the global domestic product, which would be about 10 times more. So yes, we should not be surprised. And yes, it is a drama. We are not at all on schedule to achieve the energy transition. So this is going to be the last plot, the one plot that tells it all. So here's total installed power versus years. It's a log plot. So the lines here, if it's linear here, it's an exponential growth, and then there's the rollover that corresponds to the linear phase of deployment, and then the saturation. If I just, so the black little things on the left, this is fission, which is saturated a long time ago. There are about 430 fission power plants in the world, and that's been like that for a long time. And you see wind onshore, the red squares, and you see the green triangles, that is solar PV. And they seem to be saturating. This is not a prediction, it's just saying with the present level of investments, they will saturate there at a level that is, well, 10 times too low, really. So if we want to go much higher, we'll have to invest more annually. Now you'll say, okay, so what's fusion? How is fusion going to save the world then? Well, with the mainstream, ITER, demo, you see the first blip on this graph would be in 2060 or 2070. And then there's the same growth rate, doubling every 3 years or so. Well, that takes us to the end of the century, and certainly there's no contribution before 2050. Yeah. So those private initiatives, of which there are many, of course they're smaller, and but they promise to make first fusion power in about 10 years from now. And if only one of them is successful, that would be a gain on this time schedule of about 30 years. Still not in time to make a big impact before 2050. But just in case we didn't manage to make the transition happen until 2050, at least then there's another option coming. Just to finish this argument, we also need conversion and storage. Those are also way too small at the moment, orders of magnitude. And more importantly, if you had a smart idea, there are lots of people with smart ideas, if you had a smart idea for another way of making energy, yeah, I'm afraid that would be down there. It would be in the very low power production now in the lab. And if you have, if you have to start that up, it's not going to help you by 2050. Simply because you have to build up the industry to make things bigger. It takes time. That was my talk. Fusion is not yet a demonstrated technology. If you want this transition to happen, whichever technology you take is going to take a few percent of global domestic product. You have to realize that if you build things that live long, there's going to be a replacement time at the end, and that will limit how fast you can linearly grow it. And before you even get to that, you have to build up the industry. Let me just finish by saying that most of those technologies that you've seen, like solar and wind, have just left the exponential phase. But a thing is growing exponentially with a doubling time that's faster than the energy payback time, which is the case for solar, for instance. It means that during the entire exponential growth of 30 years or so, you're using energy, not making it, you're making extra CO2. You're going to gain that back later when everything is in place and works. So it's not a criticism, it's just a mathematical fact that if you want to make the transition happen fast, you're probably going to emit extra CO2, not less. Thank you for your attention.
Great. Thank you so much, Nick, for this interesting talk on energy and nuclear fusion. If there's any questions for clarifications, just brief questions, you can raise your hand now. And in the other room, I know that Elisabeth is helping as a vice chair. So if there's any questions there, maybe she can take those. Yeah, in the back. Oh, I have to walk with them.
I have two questions. How the equivalence between human work hour and barrel of oil is established, first? And second, how much energy is used to produce a unit of energy from nuclear fusion? Or what is the efficiency of the process?
Great, thank you. Then I will first walk back to Nick.
So you just calculate the energy content of the barrel of oil, and you know that a person who's working hard produces about 100 watts. That's it. And the second question, what was your second question again?
Can you repeat very loudly?
Yeah. Yes. Efficiency of the process. Okay. No. So. Okay. The question was, I think, the unit size. So reactors produce about, well, you can make them. The smallest we can make would produce a few hundred megawatts, and the efficiency. Well, it makes heat at a high temperature, and that you have to turn into electricity with an efficiency of 30% or so. Because it also uses some power. But you could also use the heat itself, because there's a much bigger demand for heat in the world than for electricity. And that would be a very interesting option. And then, of course, the efficiency is whatever you like it to be. Yeah.
Thank you. I think we actually have to move on to the next talk, unless we want to use up the whole coffee break. But just thank you for answering these questions for clarification. Okay. Just very shortly, if you have written down any questions on the cards, the student assistants who are volunteering can pick them up, and we will select for the discussion later. Then, I would like to give the word to Mario Gianpietro in the other room, and I hope that with the technicians it will work out, and we will see it here in this room and in the other room. Yeah, great.
Hello? No way. Hello? Can you hear me?
Yes.
Yeah, but then I would like to have someone hear me. Ah? Dai, sì. Su condivisione. Condivisione. And if we go here, okay. Oh, okay. Can you hear me? Everything is okay? Good morning, everyone. I will try to be as short as possible to have more discussion. I will have to make 3 points. They are pretty different, but all relevant for the discussion. The first point is that we tend to, probably because of emotional reason, to deal with the sustainability issue not in a reasonable way. It's about emotion. It's about fear. Or we are afraid that the game is over. We will have to change our social practice, because it's amazing. We are framing the issue of sustainability with a strategy that we have to use more technology, more business model to stabilize the status quo. That is the last things you want to do. We have to change the status quo, not to stabilize. But I mean, nobody knows why we are framing. Everyone accept this logic that we have to stabilize, to do more technology, more energy, more everything. So I will start with a question with you. How are we doing with the reduction of emission? Like, let's do a quick test. How many of you believe that we are doing well? The emissions are going down? Can you raise the hand? And how many of you believe that, we are not doing well, but at least they are not growing the way they used to? Okay. And how many of you believe that they are keeping growing no matter what? Okay, that's good news. So this is an empirical analysis. These are the emissions in the atmosphere. They are registered in. This is Hawaii, but I discovered that in South Africa there's another lab. There are several labs around the world, and the curve is exactly the same. Why this is important? Because then you can map against this curve the Rio de Janeiro summit, the Kyoto Protocol, the Copenhagen meeting, the Paris Agreement. This is crucial. And basically you can see that nothing happened. It's just a sort of emotional ritual things that we're doing. We send people there. According to a fantastic strategy developed by economists, the tradable permit, those they are emitting keep emitting, but they have to give money to those that are not emitting enough to industrialize. And this strategy is supposed to reduce emissions. That unless you study the economy for a lot of years, nobody can see how this could reduce emissions. Doesn't matter. So, what is the point? That this type of information is what has been termed by Rayner uncomfortable knowledge. We discuss of sustainability, but like fairy tales. We have the zero emission, we have the circular economy, we have the fusion, we have the decarbonization. Nobody knows. Whoever makes any stupid back on the envelope calculation, see, it's absolutely not possible according to not one, but 10 or 15 different reasons. But doesn't matter, we keep going in this way. So this is something that it is important to be aware. So this is, there is no sound. Sorry. However, I mean, you could see more or less the type of emotion. There is the type of affective involvement. They saved the world. Look that they are crying. We saved them, and we saw nothing happen. Is matrix. There is okay. So, and then I will give you another video, which is exactly the same. For the Italians, do you know there is in Naples? They have every year the liquefaction of the blood of San Gennaro. San Gennaro, there is blood that is solid, but if all the people pray enough, the blood became liquid. Okay, so there is a big preoccupation for all the city, because if the blood doesn't get liquid is a bad sign. So they go in the church, and all together there, they are waiting finally when the blood becomes liquid. And when the blood becomes liquid, there is the person that you see that is now doing this. The bishop say it's liquid, and everyone start hugging each other. We did it, we did it. So what is the point? To be very, very aware of the fact that we are using now science according to the paradigm of prediction and control, that science became a new science. So if we have emotional stress, we are assuming that science can solve our problem with better technology and better things. So the second point that to me is fascinating is that there is a simple problem that we have. At the moment, we are not capable of producing food in a sustainable way, neither in developed or developing countries. But it seems to be not relevant. Everyone is concerned about climate change, but the fact that we are not capable of producing food is not considered a relevant issue. So this is the EU Commissioner for Agriculture and Rural Development that now start his presentation by saying, during my presentation, 150 European farmers will get out of job. And I don't know if you know, the average age of farmers is over 60. So basically, the farmers are disappearing much quicker than panda, but nobody cares. And they are disappearing in developed and in developing countries. So this is the issue. So what happened here? That we have two types of agriculture. An agriculture which is based on recycling, it's called circular agriculture. This is a Chinese lady that is pouring night soil. I don't know how many of you know, night soil are excrement. In China, you don't use a toilet. You use them, then they collect it, they mix it with water, and then they put it on the plant one by one. And it was a project many years ago, and then all the Europeans said, this is fantastic, closing the cycle, this is the real circular economy. And he said, but if this is so fantastic, why we are not doing it? You can ask the lady, this is me probably 40 years, no, 30 years and 30 kilos ago. And the lady answered, have you been in Paris? And he said, of course I've been in Paris. Jesus, as soon as I say so, I screw up. In fact, they say, nobody in this village ever to go to Paris, no? Why? Because we are doing this city, in technical terms, a job. And I want my daughters to go to Paris. This is the issue, that this is the killer of agriculture, of circular agriculture subsistence. So then the second story is the Netherlands. This is the Netherlands, the success story in Europe. You can see here, the red things is the Zuiderzee, the famous dam. And then because of this, they managed to get out two big pieces of land, Flevoland, the one that you indicated. And then you can see that there is another dam there, and you can see the land that is below. So they could pump more water out and get another piece of land. No, as a matter of fact, they are considering to reflood the original things. Why is that? Because one, nobody wants to go there to become a farmer, first of all. Second, thanks God, nobody wants to go there to become a farmer, because it would be a major burden of the economy, because farming is a cost. You have to give subsidy. It's no longer a source of income, and a major problem with the environment, no? More nitrogen and phosphorus in the water table. In Europe, the agriculture is the economic sector with the highest economic investment per worker, the lowest economic return on the investment, the highest environmental impact per job. Delivering service to the rural community is much more expensive, and so on. So after centuries of war, in Europe, having land is no longer an advantage. What happened? Why we got this? Exactly because of fossil energy. We saw before with Nick, the population was the same, the energy consumption the same, and at a certain point, with fossil energy having exploded. What happened? We moved from what is called an endosomatic metabolism, food making labor, labor making food, to an exosomatic metabolism, machine getting fossil energy making machine. What this has to do with agriculture? Before, the rural areas were giving energy to the cities, and then you had an agriculture that was more or less respecting the flow of ecosystems. So humans were just getting out some things here and there, pastoralists. And then we went to a situation in which now it is the cities that give energy to the countryside. And so what happened in agriculture, basically, that you kill everything alive in the rural areas, you call Monsanto, you call all the things, and you start producing in linear way things. There is no circularity at all, and basically forget about the possibility of keeping interaction, they believe Nietzsche's biodiversity and so on. So what are the conclusions? We should stop to have a reductionistic view of sustainability. It's not about that we don't have enough energy or we are making too much CO2 or whatever. It is about to learn how to be compatible with the life support system that we are getting from nature. So this is the policy legend of circular economy, that the economy is reproducing its own fund. And in reality, the discussion is different. The amount of fund you can have, how big is the economy, how much it gets consumed, depend on how many flows you get from your embedding ecosystems. So in coming to the last observation, what is the problem here? We should stop to use scientific framing that were developed in the 1800s and try to move to scientific framing available now. Stop to discuss about energy, is about entropy, negative entropy. It is not about material flow, is material flow, is energy flow, is food, is what is called the nexus, is protecting the biodiversity. It is really not acceptable to keep discussing one problem at a time using very simplistic indicator, because moreover, energy cannot be measured unless you are properly framing it in all the autocatalytic loop stabilizing the flows. And I believe that we should try to get more into a complexification of our understanding and stop to have, and I must say this, the real problem here are the intoxication of neoclassical economic narrative. We should stop to frame sustainability problems using economic narratives, because they are missing, not the elephant in the room, they are missing completely everything. They are not capable of comparing how big is the society with the ecosystem, how the interaction is a disaster. Okay, that's it.
Yes, so thank you very much, Mario, for your talk. We will move on without, for now, questions for clarification to save a little bit of time to Emilio, and he will have a talk, and then afterwards we will collect questions again on the cards. So, Emilio, the floor is yours.
Thanks. So, okay. So, my ordinary business, I am an ecologist, and my ordinary business normally is counting lizards and snakes on island, or carbon storage in plants or something like that. So, I'm quite far from this economic perspective, but I try to give you some idea exactly coming from an ecologist. So in my outline, I want to speak a little about this new epoch, the Anthropocene, and the use of energy in human society. And then I jumped to the conclusions. It's quite clear now, also in ecology, in geology, that we live in a new geological epoch. This is called the Anthropocene. Probably you know the first time that this word appeared was about 20 years ago, when Paul Crutzen, a Nobel Prize for Chemistry, he told it's a pity that still we are speaking about the Holocene, because we need to recognize we live in the Anthropocene. And since he was a Nobel Prize, he had a large audience. He recognized that another biologist used the word before, and they wrote a paper. And from a technical paper, now we found this word Anthropocene also in common language. The idea behind is that Earth has a long history of interacting systems. In the beginning, it was just a lithosphere with an atmosphere, then an hydrosphere, then also a chemosphere, and they were influencing each other. And then chemosphere became a biosphere, and inside biosphere appears someone about 300,000 years ago, more or less. And now we are at this level. The anthroposphere has an influence on the other sphere that we can consider. So this is the main idea behind the concept of Anthropocene. And now in geology and ecology, the open question is when it starts. And if we give a look to the literature, we see different hypotheses. Moving from the past, the first hypothesis is with megafauna extinction, when sapiens come out from Africa and they invade the other continent, and they lead to the extinction of big mammals. Then something else, think that Anthropocene starts with agriculture. Agriculture began around 10,000 years ago, more or less, not in the same time everywhere, and anyway had a big ecological and social consequence, because we move from hunter-gatherers to farmers, and we build houses and village and towns and so on. Something else speaks that the Anthropocene starts with the European invasion of Americas, so the new old world collision. Something else, as maybe also you showed us with the Industrial Revolution, when we start to burn fossil, to use fossil fuel, well, first carbon and then oil and so on. And something else speaks about great acceleration in the middle of 20th century. As an ecologist, it's not really important when, but that this is happening. And I want to give you something more. It is interesting that each of those hypotheses are linked to one way to use energy, different source of energy, but it's quite clear that we lead the Pleistocene extinction because we use fire. So we were hunters able to use this source of energy, and we had this global consequence, because when we lose mammoth, also the biomes of the world change. We lose the cold steppe, and the forest start to grow. Then with agriculture, we use photosynthesis and also the domestication of animals, so energy from animals, and also this lead a lot of consequence. With the use of wind, we reach, as European, we reach Americas, and the main two big ecological consequences are the Columbian exchange. We started to homogenize the biological world. We sent animal plants from Europe to America, from America to Europe and Asia, and so on. And so now it's funny that in our gardens we have probably more vegetables coming from America than from Europe. The Industrial Revolution means starting greenhouse effect, and the nuclear energy, as we use in the middle of the 20th century, means exactly the beginning of a great acceleration. And what I can say is that each source of energy. Each technology promises something, but normally are wrong. There is a simple, is an early brutal but quite simple equation proposed by Paul Ehrlich that say that human impact is a combination of three factors: population, affluence, and technology. And I think it's very simple but quite easy to understand. Obviously, technology is quite clear that if we have to transport, one option has a lower impact than the other, no doubt about that. And often when we think about energy, we think just to this aspect. But then, let me say, affluence means if I use electricity to light a room, to light a house, makes sense. If I use electricity or energy to build, as you see in the picture on the right, a ski runaway in Dubai, well, this is quite different and that doesn't make any sense. And finally, we needed to recognize that the population, the number of population has an impact. So if this square in Pisa is nice, I was working yesterday night without nobody, and it's fantastic. If it's full of people and 1 million people try to stay in this square, this is a nightmare. So I think that from an ecologist, thinking of energy is not only a question of technology. As we saw in the past, any new technology promises something, but normally new problems arise. This is an example with the nuclear fission, so not nuclear fusion, but in the beginning they promise, okay, it's safe, it's economic, it's environmental clean because no greenhouse effect, make country independent, and so, and is everything nearly not correct. So one of the points that I like is why we recognize this situation and why we are running the world. And I think the best explanation was provided by this Israeli historian, that he recognized that the answer is in our cooperation. There is cooperation also in other animal society, but normally all they cooperated in very large number, like insects, but they are not flexible. Bee cannot kill the queen and establish a republic of bee or something like that, or they can cooperate very flexibly, but in small numbers. Like chimpanzee cooperate very well, but in small number. They need to know each other, otherwise it's impossible to have a cooperation among chimpanzees. And we are the only species that can cooperate in large number with a high degree of flexibility. And why this? Harari say is our imagination. And this also was explained very well by an Italian ethologist that recognized also, for instance, chimpanzee can have an imagination and build something, but there is a limit. I show you this picture in black and white, was an experiment of a chimpanzee using tool in a zoo. And this chimpanzee in the picture was the most intelligent among this group of chimpanzee. His name was Zoltan. He was able to build a tool in that way to reach banana or something like that, but he never was able to build a tool, to build another tool to reach a result. So this is a limit that we don't have, definitely. And Harari explained that this is because we live inside a dual reality, a physical reality, something that we can see, we can smell, we can eat, and works. But we have also built a fictional stories with a lot of fiction that we believe is such a money, corporation, nation, and so on. And when all we believe in the idea that a worthless piece of paper is we can buy 10 banana, and everyone believe this. Oh, okay, this works. So maybe an hypothesis to the challenge to environmental change we have is that we must become better storytellers than wizards such as bankers or lawyers. And just some other conclusion, and in this epoch, there will be certainly a new geopolitics led by population number. This is quite clear, and I think as a European, is evident that we become irrelevant. Also, all that we call ecological transition means in new geopolitics, we need to be aware. This is an example now in blue country that are most productive for natural gas, and in red country that have more rare minerals. And it is quite clear that in this energetic transition we need those minerals, and so something will change for sure. And it's quite evident that if we don't care about how we extract those raw minerals and so on, well, we will have other problems. And I think our problems cannot be solved at national levels. And also there is no planet B. The idea that we go on Mars or something like that is quite wrong, and maybe works for Bezos, but just for him and nothing more, and I'm not so sure it's a good option. Also, in storytelling, I think we must suggest that limits can be also an opportunity. In the industrial history, in some cases, when we had a limit, we open a new perspective. So this is can be quite interesting to say. And finally, partially in contrast, waiting for the best solution also has a big cost. So we needed to consider that. Well, thank you for the attention.
Yes, so thank you very much for this interesting talk. Before we move on to the last talk by Yamina Saheb, we will set up, because she will be joining online, we'll set up her presentation if the technicians can take care of this. Then the student assistants in the blue shirts will walk around to collect your questions. So please give them your questions to them on paper. And I will move to the other room again for the last talk. And then afterwards, we'll have the discussion with the questions. Okay, so welcome Yamina. Very nice to have you here. The floor is yours. I hope that everybody will be able to see. Yeah, the PowerPoint is up. We can see your face. So the floor is yours, Yamina.
Good morning. Thank you, Jan. Thank you for the organizers for the invitation and the opportunity to share with you the main findings of the last IPCC report on sufficiency. So the IPCC is not, as you know, not a research center. Scientists involved in the IPCC report assess what is in the literature, actually, and summarize what is in the literature for policy makers. And there are 3 reports in the 3 working groups. One is on physics of climate, one is on adaptation, and the last one is on mitigation. And it is in this report that was published on the 4th of April where sufficiency has been highlighted as one of the solutions that we should be looking for. So the important point from this report is that sufficiency is now defined in the summary for policymakers of the IPCC report. Without this definition, we were facing facing an issue at international level, both in scientific community and in the policy discussion about what sufficiency is. And when you look at this definition, the three or four main points about the sufficiency definition included in the IPCC report is the fact that sufficiency are all the measures or the policy measures and daily practices that avoid. The fact that avoid instead of reduce is very important. Avoid at the first place the demand for energy, materials, land, water. So it goes beyond energy issues, because if we look at climate mitigation, by focusing only on energy, we will not be able to decarbonize, because very often the energy consumption is the result of, for example, the infrastructure that we have already put in place. So we locked ourselves with the infrastructure. And at the same time, so that's the first important point in this definition, the fact that it avoids the demand for all natural resources at the first place. So it goes beyond energy, and it's about avoiding the demand. And then the second important point in this definition is that sufficiency is not is about delivering well-being for all. So it does not matter if you are in Paris, Dakar, or New Delhi or Washington DC. So the need for people, all the humans, for well-being is the same everywhere. And this, I think, would be game changer in the future in policy making, especially in international collaborations, but also in scenarios modeling the 1.5 degree target. And this delivering this human well-being should be done within the planetary boundaries. So we should not overshoot the planetary boundaries. Combination of these three principles in the definition of sufficiency should in the future make an important contribution to policies in the climate mitigation sphere, but also in climate scenario spheres. But, however, the fact that we have a definition, that does not mean that we won the battle and sufficiency is going to be mainstream. From my perspective, the fact that we have a definition is just the starting point. And you will see in the next slide why it is just the starting point. So if you look at then, you search for the word sufficiency in the IPCC mitigation report. And as I mentioned earlier, IPCC authors do not do new research. They just summarize what is in the literature. So you will see that in most of the chapters, and unfortunately in the framing chapters, like for example in the introduction framing or chapter 13 on policies, the word sufficiency does not appear at all. It's not in the literature. And that's why it does not appear in the IPCC report. However, it does appear in some of the chapters. It appears mainly in this case in the building chapter, because there has been, when you look at the literature on sufficiency, most of it has been two-thirds, the focus of two-thirds of the existing literature until 2020 was on housing sector more than any other sector. Then to some extent there is a bit on mobility and a little bit on food, and all other sectors are not do not make a link between sufficiency and how to decarbonize these sectors. So you see that the road is bumpy to make sufficiency mainstream, even in the chapters where it has been mentioned. So, for example, chapter 5, which is for the first time in the IPCC report, we had a chapter on the demand, on reducing the demand in demand services. In this chapter, unfortunately, sufficiency has not been highlighted as much as it could or should have been, because of the lack of literature and maybe for other reasons as well. But the most important point is that the framing and overarching chapters, for example, mitigation, near-term mitigation options, sufficiency does not appear at all in this chapter. It is unfortunate, but this is the reality that we are facing today. So there is still a lot to be done. And then, sorry, oh, I cannot see. Oh, sorry, I had the graph here. It looks like I do not see the graph. If the technician could bring the graph back. So can you? And here as well. It looks like we do not see the graphs in the presentation. I don't know if the technician is hearing me. So what we try to do is to assess the sufficiency potential, or identify how the sufficiency potential has been assessed in the literature. And what we see is that, you should see it here, Or maybe I could share my screen differently. Does this work if I do it in this way? Yeah, it looks like it's going to work. Yes, so if I go to this one, yeah, I guess you are seeing my screen. I cannot see you anymore, but you should be seeing my screen. Trying to assess the sufficiency potential in the literature, we see that it's not always, even if sufficiency is there, it's not always labeled as sufficiency. So there is an echo. Do you hear me?
Yeah, sorry.
Can I continue?
Yeah.
Okay.
Just to say, if you want for people to see the graphs, the technicians are saying that you have to share your whole screen and not just the PowerPoint. So maybe stop sharing and start anew, and then hopefully it will work.
Okay. Do you see it now?
Yeah, yes, perfect.
Okay, so what we see here is that one thing we need to keep in mind is that even if sufficiency measures are included in some of the scenarios, they are not necessarily labeled as sufficiency because sufficiency was not identified as one of the pillars of the decarbonization. And we are hoping that with the progress made by the including definition in the IPCC report, this will change in the future. Overall,
what
we need...
Yeah. Amina, could you maybe share the presentation? Start the presentation, the PowerPoint, because now we just see it very small.
Okay.
Yeah,
is it
perfect.
better?
Thanks.
Okay. So the point is that overall, to reduce to the combination of the demand side measures could contribute up to 70% to reducing emissions by 2050. And when we say demand side measures, this means sufficiency measures and efficiency measures. Unfortunately, even in this figure, we did not label it as sufficiency, but instead it has been labeled in two subcategories: socio-cultural factors and infrastructure use. This all falls under the sufficiency concept, and then technological improvement, which falls under efficiency improvement, under efficiency measures. And of course, we see that given that sufficiency was absent from the research and from policy making in most of the countries, that's why we see higher potential for efficiency than insufficiency measures. We think that these figures will change in the future because and will be more balanced, and the sufficiency potential will be more accurately estimated. And the evidence for that is, for example, for buildings, for housing, we were able to estimate using the decomposition analysis the contribution of sufficiency to decarbonization. So between 1990 and 2019, emissions from housing, global housing stock, have increased, and of course, efficiency measures, have contributed by reducing emissions by around 49%. But the lack of sufficiency measures have led to an increase of emissions that is by 52% increase of emissions. So we see that the efficiency improvement, the contribution of efficiency improvement to reducing emissions in housing has been more than fully offset by the lack of sufficiency measures. And this is part of this. This emission increase is usually labeled as a rebound effect, but actually, when you look at the details to the literature on the rebound effect, most of the rebound effect, the direct rebound effect, for example, in housing, would not have existed if we would have had sufficiency policies. Now, looking to the future, we used three different set of scenarios. The International Energy Energy Agency scenarios, and then two scenario from image that is labeled as lifestyle and renewable scenario, and then the last scenario is resource efficiency and the climate change scenario. In the case of something that is common to all these scenarios is if with the current with business as usual scenarios or with the current policies, sufficiency are not taken into account, and this leads to an increase of emissions. Most likely, you see in the IEA case, they estimate this at 54% increase. It is when you decompose, you find out that it's 54% increase. In the two other scenarios, it's a bit less, but most likely the IEA current policy scenarios is the most accurate scenario, reflects better the reality than the two other scenarios. And then, this is for if we continue with the current policies. But even in the scenarios aiming to 1.5 degree target or compatible with the Paris Agreement, this IEA sustainable development scenario is around less than 2 degrees, and this one is for 1.5 degree target. In this case, the IEA does not consider any sufficiency measures, so there is no contribution, and this potential is lost. And instead of decarbonizing through the demand, so the solution is to decarbonize the supply and to consider negative emissions for the decarbonization. In this scenario, they considered sufficiency measures, but only in the global north, because part of the literature had an issue with understanding that sufficiency could apply and should apply for both the global north and the global south, but not in the same way. And that's why we have this scenario, for example, where they considered sufficiency measures only for the global north, and in this case sufficiency contribute, but the contribution is quite small. In this scenario, they consider sufficiency measures for both the global north and the south. However, in this scenario, we have only thermal end uses. Electricity was not included at the time we were working on the composition of this data. But importantly, we see that if sufficiency is considered, so it will contribute to reducing emissions. And this is why we do think, based on this work, that the contribution that not only that we need to consider sufficiency measures in the policy framework, but we also think that in the future we will have more accurate data showing the potential for sufficiency is much higher than what we have been able to show this time in the IPCC report. So basically, for the youngest one, this is an open research field or where there is a lot to be done. The IPCC report opened the door for something that is sufficiency as a concept is not new, but considering sufficiency in climate policies as one of the pillars of the decarbonization is quite new at global level. And this is an open door and the call for all the young researchers, and not only the youngest one, to consider sufficiency in their work as much as possible to contribute to the decarbonization of the global energy system, the global system economies. Thank you. I am not hearing you anymore.
Now, do you hear me now?
Yeah, I do hear you. Yeah, now I hear you.
Thank you so much, Amina, for your talk and your contribution to this conference. Now I will ask the volunteers to collect the last questions so that we can select some more for the discussion. So now we have about 25 minutes, actually, or 20 minutes for some questions, and already so we have selected a few questions from the audience to discuss. I hope that this will work with the technique that we can have both speakers in the rooms talk. Okay, super. So while the rest of the questions are being collected, I will already start. So yes, sorry. What is? Do you want to ask something, or we will do it on paper? But yeah. So I will start with the first question that we have collected, and this one is addressed to Nick. It's about the political economic challenges associated with this development. What do you have to say about the political economic challenges related to the risk of concentration of wealth and power associated with fusion energy?
That's an interesting question. Well, it is very likely that a lot of technologies, including fusion, which is very high tech. If I speak here, yes, better. It's quite clear that a lot of technologies, especially high tech, like fusion, is likely to be of profit to the richer countries first, and yeah, that definitely is an issue. So I think if there's a shortage of anything such as energy, that is going to be a political and a power game too. So no, I'm not happy about that, but I also don't know what to do about it. Let's say those technologies that are much more democratic, like that are spread out. But we have to realize that more than 50% of the world lives in mega cities. So it's not like outside the global north, everybody lives in rural societies or anything, not at all. But where the population is spread out over larger areas, of course, the distributed energy sources would be the obvious choice. So that would spread power, I think.
Great. Thank you, Nick, for your answer. I will actually go and ask Mario, or Emilio, or Yamina if you have something to add to this question about the political economic challenges associated with this new technology, with nuclear fusion. Does one of you want to add something?
No, I believe that the situation now with globalization, the way the market is operating, and the fact that this is a completely new technology, nobody can make any prediction. I think that Nick is right in making his point.
You have to speak more closer because they can't hear you.
But I think that we are dealing with something which is quite unpredictable. This will be the problem in the future. Whatever you do, you have an hyper cycle, and then the rich become richer, the poor become poorer. In this case, you have a combination of not only making more profit, but controlling more power. So what can happen, nobody knows. It's really an explosive mix. No?
Yeah, I can add another observation. Just in those years with the vaccine against COVID-19, the idea is, well, it's quite clear that a totally free market situation doesn't work very well because, okay, we have the first and second, third vaccination, but part of the world still is waiting, and obviously this is not really intelligent also for us because we are growing new variety of COVID-19 in that way, and well, it's quite clear. Okay.
Thank you. Yamina, do you want to add something, or should we move on to the next question?
You can move on, and I can come back for about the political economy. I think of the whole decarbonization, not just the fusion, later on.
Yeah, exactly.
Great. So the next question is specifically to Mario. It's written, you argued that uncomfortable knowledge can help expanding the scope of sustainability discussions, but by definition, this kind of knowledge is not accepted by institutions in power, for example, the government, whose role in building sustainability transitions is crucial. What opportunities do you see for uncomfortable knowledge to overcome this challenge? Mario.
We had during the summer school a discussion about that. I was complaining about the young generation that they are basically accepting the master narratives given by the establishment that we need more investment in new technology, more business model, doing the war against climate change so that the bank can finally get more money. And what I was saying that young people should protest, should try to propose something different. So I would say that the young people should stop accepting using the narratives that are proposed by them by the establishment and thrive on uncomfortable knowledge. Get as a matter of fact, I can do some free publicity. We have a hub, uncomfortableknowledge.com, in which we presented the result of a big European project about the narratives, the very bad quality of the narrative used by the European Commission. And I believe that we cannot have Greta as the only person that is fighting the official story of the establishment, because this is a losing strategy. We don't have a problem of climate change. We have a problem of a sustainable a pattern of development which is not sustainable, and nobody is addressing the problems. We are just remaining in a sterile discussion, and kids should, or yeah, I'm old, so I mean you are all kids for me. They should make accountable the institution about the policy legend that they are using. It is not acceptable that people accept the circular economy. The economy cannot be circular. It's against the thermodynamic laws. We have a plan A to save the world that is based on something that is against thermodynamics, and nobody says anything. We are all talking, yes, circular economy, or decarbonization in 10 years. It's ridiculous, but nobody protests. I mean, all the kids, they are vegetarian, and being vegetarian will not scare the banks. As a matter of fact, they are very happy because they can make more products vegan coming from Peru, refrigerated airplanes. We have to challenge the storytelling that the power is giving to us. This is what the young people should do. Whereas they are buying all the package completely. That their problem is to get more technology, a more business model to stabilize what we are doing.
Thank you, Mario. Is there anyone else of the panelists who want to add something to this?
May I react? Because, yes, I agree, Mario, that the younger generation should have every right to protest and bring the governments to accountability. And then suddenly you say, but vegetarians aren't saving the world either. I didn't quite make that jump. Are you saying it's bad to be a vegetarian? Are there any vegetarians in the room? Vegans?
Yeah, there are a lot.
Not a lot. Okay.
Okay.
Well, you definitely not good for the planet.
Yeah. I can give you a very short answer. The area of China and the area of the United States is the same. In one area, there are 1.5 billions, in another 400 millions. Why? Because they were mainly vegetarian. So if you are vegetarian, you have more people in a place because basically you are stocking more people. In relation to the consumption, 80% of the consumption in the food system goes in the post-harvest. If there is a food which is a disaster in the post-harvest, it is vegetable. Vegetable, you are bringing around water, and with 50% of losses, you have to clean it, you have to have packaged in plastic. The vegetables are usually transported very long distance because not everyone can have fresh vegetable. So really, I don't know whether it is better or is not. For sure, we should stop eat all the meat that we are eating now. You can make rules that you cannot have feedlot. I will be in favor of that. You can have meat once a week or once 2 weeks, no problem. But what I don't like is the reductionistic idea. It's like the energy, the things that if meat is bad, the vegetable is good. No, everything is complex. You have to be responsible and try to arrange social practices in a way that are makes sense. Why we are eating all this meat? Because of the agriculture in developed country has to be based in animal production, because then you can externalize the production of feed elsewhere. Europe imports 83% of the feed. So basically, if you are running a farm, you can use your technology, you're milking cows every day. If you would use a tractor, you use the tractor once a year when you are harvesting. So this, by the way, this was one of the Georgescu region discussion. This is why agriculture is not economically viable, because the plants go too slow. So then we move to animal production because we can import. And as a consequence, we are overflowed by meat. This is bad, yes, but it's not that meat is bad per se. It's the system that is not sustainable. I don't know. As I am,
Mario, can I ask you to wrap up, and maybe Yamina wants to react as well?
Yeah, I think that, I don't like too much when we put the responsibility on the youngest ones. I think the youngest ones have a role to play because it is their future, but we do have the responsibility as the oldest ones to empower the youngest ones with the right knowledge, with different things. And I don't like too much that we do not take responsibility for our contribution to the system. We are sitting comfortably in our career, in our age index, etc., and we do not question too much what we have done and what we could do I consider that we have depth. My generation had depth vis-a-vis of the youngest ones, because we have contributed to maintaining a system that we knew was not sustainable. At least since the Rio conference, there was no doubt. So the Rio conference, I was at high school during the Rio conference. So all my career, all my education has been during a time where the unsustainability of the system that we were raised in was known. But we did continue in the same thing. So I would say that instead of putting the responsibility of on the youngest ones and blaming them, they have no. It's not their fault. It's our fault. We should take responsibility for what we have done. For most of us, have been the fact that we have been silent during all this time, and the fact that we contributed to sustaining a system that is not sustainable. And then working on empowering the youngest ones, and working on paying our debt for the youngest ones by contributing to changing the system, to the metamorphosis of the system. Thank you.
Thank you, Yamina. Okay. So now I would like to bring the discussion back a little bit more
John,
on topic.
can I just clarification? I'm not blaming the young
future
people.
of energy.
Yeah, what I'm saying is that
But
they should.
Mario,
I'm not blaming the young people. What I'm saying is that they should do something else. And then, moreover, I mean, you don't know probably my career. I have been never happy with the things, and I've been always fighting every possible aspect of the system. So I don't know. I believe that I would strongly recommend to young people to adopt a different strategy for fighting for sustainability. That's it. Okay. I'm not blaming them. It's nobody's fault.
Okay, thank you, Mario, for your last comment. I have a question for relating to the topic of fusion. It reads like this. Private initiatives rely on decades of publicly funded and publicly available research. Thus, the rise of private initiatives mean a reduced stream of public knowledge about advances. I think, Nick, I will give the word to you.
Yeah, well, that's of course what always happens with new developments. The iPhone, whatever you want, is built largely on knowledge that was generated with public funds, and then at some point companies start to make products and patent things that they add to it. But the nuclear fusion program in the world has been unique in the fact that all those countries are developing it together. It's the only program where some sensitive technology or interesting technology has been shared openly with all those countries. since 1958, when the Russians came out to the Atoms for Peace conference and said, this is so difficult, why don't we put our cards on the table? Since then, it's been a world program.
Okay. Thank you, Nick. I actually will now move on to two interesting questions that relate to each other, addressed to Yamina. The first one is, I'm sorry if I missed it while you were talking about how exactly sufficiency is measured. I do not know much about it, and that is why it sounded a bit abstract to me. It goes together with the question, could you provide an ample example of policies to be applied for sufficiency in several sectors, like in industry?
Yes, so examples of policies, of sufficiency policies, are for, if we look at land use and urban planning policies, these are the policies that make the sufficiency happen or to avoid the sufficiency to happen. I give you an example. In Luxembourg and at the EU level, we have a voluntary target to limit the use of land. But in some countries, it is implemented on mandatory basis. So, or in some cities or some regions. So, for example, in Berlin region, it is on there is a requirement that you cannot go beyond the certain level of use of land. As a result of that, if there is a new development in Berlin area, for example, so they will push more for new development of multi-family buildings instead of single family homes, because if you have single family homes, you will need more land, and you also need more materials, and you also need more energy and more water, etc. So this is one of the policies that we identified that leads to avoiding the demand for energy, materials, land, and water at the first place. And then how to measure that in practice? In practice, it is measured for this policy, the effect of this policy, it is measured by the floor area per capita. Just to give you an example, so the floor area per capita has been kept growing, increasing in OECD countries. Today, the average floor area per capita in North America is around 60 square meter per capita. In the EU, the average is around 40 square meter per capita, while in Africa, it's less than 10 square meter per capita. So you see, there is a huge discrepancy between different world regions. Unfortunately, scenarios aiming for 1.5 degree target, except two scenarios that we identified don't do that. There are 230 scenarios aiming at compatible with the Paris Agreement, so between 1.5 and 2 degrees. And in almost all these scenarios, they consider a continuation of the increase of the floor area per capita everywhere, but they still consider this discrepancy between the global north and the global south. So they project most of the scenario, well, the most known scenarios project by 2050 that if you are in North America, you would have 65 square meter per capita, but if you are in Africa, you would have 10. So it's good. We are allowing you to have 10. You see, this is not at all realistic because the land is already overtaken in OECD countries, overused, overwasted, while it's in these countries where we should first start and where we could avoid the use of more land, because we already have enough square meters that are built. The consequence of that from industry perspective is, if I focus only on the construction industry, this means that the industry today, the construction industry, is making profit out of constructing new buildings. So they know how every year they have projections for the number of new square meters that they will going to build, and this is so they lobby a lot our policymakers to allow them to build as many square meters as needed. But in reality, in most of OECD countries, we don't need we most likely we don't need to build more square meters, or at least we are sure we don't need to build as much as the industry is projecting to build. Why? Because we have so many square meters that are not used. That was the case before COVID, and with COVID, the number of unused square meters that are already built has increased everywhere. So, for example, in Rotterdam, in New York City, there are programs to shift, to repurpose the existing constructed buildings for today's needs. And today's needs are today I am intervening from Paris. So today's needs is not just a house where you could live, but also nearby place where you could work, a nearby place for your kids, etc. And this is a big change for the industry. So of course you can imagine that the real estate industry and the construction industry is going to fight back, and they are going to lobby very hardly against this kind of measures.
Yes, thank you, Yamina. Then there's another question, and I think this one will be interesting for all the panelists, but it's addressed to you again, Yamina. So maybe if you can start, try to keep it in 1 minute so that we can have the other panelists before we finish. So it reads like this: low energy demand requires much higher energy prices, which is a democratic challenge because this hits the poor. Do you think low energy demand needs to be combined with tax or dividend or universal basic income?
When we say that low energy demand is means also high energy prices, this is in the current economic system. So the first thing, the low energy demand cannot occur in the current economic system. Shifting to low energy demand means also considering the justice issues and the access for all for energy services. And instead of talking about the access to energy, we should talk about the access to energy services, because for our well-being, what I need is today, because it's very warm in Paris, what I need is a comfortable room from thermal perspective. I don't really need an air conditioner. I don't need a fan. I don't need providing us with comfortable houses, for example, does not necessarily require energy. It requires energy in today's world because we made so many mistakes in the past. So when you rethink, when you consider sufficiency and you rethink, it's really metamorphosis in the mindset and in the policies, and it's also metamorphosis for the scientists. Then this question will not come up anymore. Thank you.
Is there anyone else, Mario or Emilio or Nick, who would like to comment to this? I see Mario. Yeah. Go ahead. We can't hear. 1 second.
Not imagine that the looking for alternative social practice that are more sustainable using the market. This is a wrong idea. This idea of the behavior, we do not have a behavior. We are social practice that depend on our household, our community, our friend, and then if you want to change the way we do things, if you are using the market, you are stabilizing the actual status quo, more or less of the same roles. We have to do new roles. So these type of things, in my view, cannot be obtained with business models. That's it.
Emilio or Nick, do you want to add maybe a last comment? I think this was the last question, so if you have anything to add, please go ahead.
So on this question, I totally agree with what the previous two speakers said. But for the minute, if energy is scarce, it's going to be more expensive, as we see today. It has a lot of bad effects. It's not giving the right incentives. I totally agree with that. So how are we going to implement this other set of incentives, other thinking at government level, so to stimulate the correct policy?
Yes, thank you. Emilio, do you want to add a last word, or Yamina?
Yes, please.
Go ahead.
Yeah. I think when it comes to energy, it was a big mistake, and all essential services to privatize, to put them in the market. And today that we are facing crisis, my hope is that we will get them out of the market, because it is the duty of governments to deliver on the essential services to all citizens. And putting energy and education, health, etc., in the competition in the market is just a mistake. And I would say this is how we fuel the extreme right, and this is how we fuel the wars, etc. So let's use the opportunity, and fortunately I call it an opportunity of the Ukraine war, to get back the power to the citizen by getting back the essential services out of the market.
Yes. So thank you everybody for being here. If you have written down any more questions, you can hand them to the speakers, and they will have opportunity for more reflection. Thank you very much, Nick and Yamina and Emilio and Mario, for being here. And I hope that we will that we can continue this conversation. Thank you, everybody.